Okay, so we're going to carry on with the topic of hypothesis testing. Um, this topic of hypothesis testing, as I have mentioned in previous sessions, it can get complicated if you begin to lose track of what terms mean or what terminology means. So what I would advise is that as you follow along today and also going forward at the next session, if at any point you find there are words being used where you just literally don't know what they mean. So examples of that will be test statistic, population parameter, random variable. Make sure that you do sort of pause, ask what the word means or find out what it means, because the big overarching theme of hypothesis testing is it's not actually that complicated in terms of calculation. It's more about understanding what words mean, understanding a process. So just keep that in check, because I'm sure there'll be some of us that find this topic a little bit tricky, because it might seem a little bit less mathematical and a bit more wordy. But I promise you it's not as bad as you might think, as long as you give yourself the opportunity to find out what any words that you don't know what they are, you find out what they mean. Okay, so an example of one such word or one such pair of words is a critical value. So this is something I'm going to add to our list of terminology within hypothesis testing. And then once we've understood that a bit better, critical values and what they are, next session we'll finally look at the full recipe for how we do a hypothesis test, which will hopefully refresh a little bit of what we've done before. So this session is just on this concept, critical value. So we're going to find out what a critical value is and how we calculate it. So to start off with, I've asked a few similar questions like this before, but this one is specifically targeted at thinking about critical values. So I claim I have a fair six-sided die. So I walk up to you, say, here's my die. I promise you it's a fair die. Let me prove it to you. And to prove it to you, how am I going to prove it to you? I decide to roll it 60 times. So I roll it 60 times and I say, count how many sixes I get. And you're going to count how many sixes I get. And if I rolled a die 60 times and I got 10 sixes, would you believe it's fair? If I rolled it 60 times and I got 60 sixes, would you believe it's a fair die? And to be honest, I think we can answer those now together. It should be quite simple. 10 times, I think it would be reasonable to think it seems fair. That's what I would expect. I'd expect about 10 sixes out of 60. If I rolled 60 sixes, I would probably think that seems astronomically unlikely. I think that die, you've rolled it 60 times, you've got a 6 every time, it's probably biased. It's not a real die, or it's fake, or it's modified in some way to only give me sixes. So the question is, what number between 10 and 60 do you think is the deciding point? Because we've got a spectrum of opinion here. We're saying if I got it 10 times, it seems fine. 60, definitely not fine. So where is the middle ground here? Which number am I going to take between 10 and 60? So I will give kind of an answer to this on the next slide. But before I do, pause. First of all, make sure you understand what the question is asking you. And then second, see if you can think of a number that you think would be reasonable. And then we'll see if you're right. Pause the video now and have a think. Okay, let's take a look. So I've tried to illustrate this, basically mocked up in Excel what is the probability of rolling a specific number of sixes out of 60. So to clarify what we're looking at here, on the x-axis you've got a number from 0 to 60, right? Which makes sense. If I roll it 60 times, my possible outcomes, there are 61 outcomes, and it's that I get 0 sixes, 1 6, 2 sixes, and so on, up to 60. Those are my 61 possible outcomes. Each one of those outcomes on the x-axis has an associated probability of happening. Now really this shouldn't quite be a line because this is a discrete distribution, isn't it? I can't roll 1.56s, for example. So really this should be a set of dots, 61 dots that form this line. But I've drawn it as a line for now, just to make it a bit easier on the eyes. At each value on the x-axis, you've got a probability. For instance, around here, where the laser is, I've got 5 6s. What's the probability of rolling 5 60s out of 60? It's about, and I go up here, 0.03. Right, about a 3% chance. If I were to add up all of those 61 probabilities, I should get the number 1 because they are all completely mutually exclusive outcomes. And then let's just check the features of this make sense. At 10, there's a probability of about a little bit less than 0.14, right? So 0.14, 14%, it's not actually that likely to roll to exactly 10 sixes. It's 14%, but out of all of the outcomes, it is the most likely. And that makes sense. 10 is extremely likely, or at least, sorry, not extremely likely, but it's the most likely out of all the outcomes. And then on either side of that, it drops down, doesn't it? So if I roll 9 or 8 or 7 sixes, that's getting less and less likely. By the time I get to 1 or 0 sixes, it's pretty unlikely. And then let's answer the actual question on the first slide. At what point does it start getting really unlikely to have rolled that number of sixes? At least graphically, at around 20 sixes out of 60, I get pretty close to 0. And from then on, it's almost like a flat line. Now, if you zoomed in, it's not actually a flat line. It's a very, very sharply decreasing line. But you can't have a probability lower than 0. So it's going to asymptotically get closer and closer to 0 here, really. So if your number on the previous slide was, say, 40 or 30, I would say probably doesn't have to be that high. Already by around 20, it seems like it's a biased die, right? Now, to be completely clear here, there's nothing actually special about 20. Happens to be a multiple of 10, so it shows up on the graph. But we could say 21 or maybe 18, right? So something in this region here, around about here, this is where we have a boundary between what seems unlikely and what seems almost impossible. And the specific number we end up choosing, that is what we call the critical value. Okay, so the number I was asking for you for in the previous question was, what is the critical value of this scenario? Okay, so let's just clarify this a bit more technically, and we'll describe it more technically on the next slide. So I want to keep this example still in mind, and I just want to start writing down some actual mathematics to describe what's going on, so we remember to get used to the notation, so it's not all too wordy. Right, so first of all, let's talk about the test statistic of this scenario. The test statistic is the thing which we're measuring, right? So let's write that down first. So our test statistic, and I'm going to call it in this case X, is what? It's the number of sixes rolled out of 60 die rolls. Okay, so we have to be very specific. Someone needs to understand exactly what you're measuring. I'm rolling a die 60 times. I'm going to count how many sixes I get. That is my test statistic. In this specific case, X ranges between 0 and 60. Okay, just something to keep in mind. It should be obvious, but the X is the number of successes. The number of sixes should range between 0 and 60. So that's the test statistic. And what is the distribution in this case? Well, by default, if we assume it's not biased, right? Assuming it's not biased, we're going to write the following. X is modeled by a binomial distribution where n is 60 and the probability of a success, rolling a 6, is 1 in 6. Okay, so that's important there. We've defined the binomial distribution which applies to our test statistic. And that's what would effectively allow you to generate this graph, is if you know this specific set of parameters. Okay. And what's our population parameter? This is our population parameter because it is the number that describes the behavior of the die. It is the number which tells me if it's biased or not. Right? By default, I assume it's a sixth. If I assume the die is biased, it might not be a sixth. Okay, so that's the population parameter, and this one here is the number of trials, which is 60. Okay, so I haven't talked about critical value yet. We will in a moment, but I just want to make sure we review a few of these words that we learned last time. Okay, right, so now we want to more formally try and define what exactly is this critical value. Now, before I wrote down all of that technical stuff, just by eye, we could see the critical value, let's call it C, seems about, let's just write approximately equal to, it's approximately equal to 20, right? But we want to be more rigorous. Why 20? Why not 21? Why not 30 even? Why not 15, right? 15 is still, quite unlikely. So what we're going to do is we're going to define it based on a significance level, right? So we learned about significance level before. A significance level will be a percentage, such as 1 or 5 or 10, and the question will usually give it to you. And it defines how willing you are to accept an unlikely result, and it effectively defines the critical value for you implicitly, right? So let's just pick one. Let's say I choose a significance level, or the question that I do gives me a significance level of 5%. Okay. What that means is you're going to take the 5% you're going to take the sum of the probabilities of the most extreme values over here, and you're going to add up all of that. So probably we'll have to go a bit further actually, maybe up to here. You're going to add all that up until you get 5%, and at the point you get 5%, you're going to define the boundary as being the critical value. To be a bit more specific, we're basically going to say the probability that the random variable in this case is greater than or equal to my critical value is equal to 0.05, where that's the significance level. Okay. So now we've defined it precisely because we know what X is. It's defined by this binomial. We can calculate stuff like this, right? We can calculate the probability that X is bigger than some number. And then all we have to do is think, right, what is the number C such that the probability of it being that or more is 0.05? And it's a bit like saying, pick a critical value C so that all of the probabilities here correspond to 5% of all the probability. Okay, but really this is your implicit definition of the critical value. Implicit meaning it's not in the form of C equals something. The C is embedded within the formula and you can work out what it is by trial and error, and we'll talk about that in a moment. Okay, but at this point I just want you to be clear on what the critical value is. It's the number such that the probability of your test statistic being equal to or exceeding that number is equal to the is equal to the significance level. Okay, cool. Right, there's one thing to be said about this though, which is y greater than or equal to, y not less than or equal to, and the answer to that is it depends on what you're testing. So if you think back before, when we talked about one-tail tests, we said there were two forms. There's one where you're checking if the population parameter is greater than or equal to, and there's another where, or just greater than, and there's one where you're checking that it's less than. So there are two types of one-tail test. There is the greater than version and the less than version. And hopefully, visually, if I just get rid of this, we can see on the graph where this number 2 comes from, why there are two types of one-tail test. It's because there are two extremes on the graph. Where is all the unlikely stuff? The unlikely stuff is over here on the right and also over here on the left, right? And that's why we use the word tail. So this is a tail and this is a tail. In terms of our example, what that means is 10 is a really likely, is a reasonable answer to how many 6s I roll. If I roll 20, that's pretty unlikely. However, if I roll just 1 out of 60, that's also really unlikely. So there are two different tails. If you're doing a one-tail test, it means you're only testing one of them, but your critical value will depend on which one you're testing, right? If I'm testing that tail, then my critical value will probably be something like 20. If I'm testing this tail, my critical value will probably be something like, 1 or 2. So there are two critical values, right? So what we can do is, let's at this point just give them a name. Let's call them the one on the left C1 and the one on the right C2. Within this whole topic, when you do a one-tail test, there are two possible critical values to choose from, and you have to choose the appropriate one. And if it's a one-tail test, then the C2 is defined as follows. Let's call it S, where S is significance level. So the probability of being greater than or equal to this C2 is your significance level, and the probability that you are less than or equal to C1 is equal to that significance level. Okay, but you only pick one of these, right? Because it's one tail. For one tail test, pick one. And the one you pick will depend on the question, which when you start to see the questions, you'll get a feel for which one you're supposed to choose. Okay, so hopefully you've got an idea of what the population parameter is. It's effectively a value on this x-axis in the probability distribution, and it's that value at which, if the test statistics exceeds it, it's really unlikely. It's the significance level. It's 1% or 5%, whatever you've been given, or it's less than for the C1 version. Okay, so now let's look at how we calculate it. So let me rewrite again the two cases. Okay, so we're going to stick with one tail for the moment. For one tail, case 1 and case 2, you will do one of these. You're going to say this or this, and S equals the significance level. Okay. Now, you might already have some idea on how you're going to calculate this. Unfortunately, at this stage, there is a smart way to do it, and there's a slightly simplistic way to do it, and we're just going to learn the simplistic way for now. And that simplistic way is to use trial and error. Okay, so let's pick one. Let's say we're going to do this one here, case 1. Now, I can't show you the calculator, but I'm going to kind of describe what you'll be doing. You are going to go on your calculator and you're going to use the binomial CD function. And what you would then do is you would say, okay, I know what my significance level is. Let's say it's 5%. So that would be 0.05 here. And then you would say, I know what my x is. For instance, in the prefixes example, it has an n of 60 and a p of 1/6. And you would just keep trying values of c until you get less than that significance level. To just try this out, let's do a specific example to make sure you understand what to do. So let's do an example. Let's say, well, let's do it actually. Let's stick with our dice scenario. So n is 60, number of trials. P is a 1/6. Let's say my significance level is 5%. Remember, that's the same as 0.05. And let's say I want to find the lower tail, the one on the left. Can you find what the C1 value is? Use the binomial CD function. Okay, so I'm just gonna, you can start doing that now. You can pause and maybe skip me. Alternatively, I'm just going to describe the process of me doing it, so you can kind of follow along if you want. So I've gone to the statistics. I'm using the calculator. I've gone to statistics, distribution, dist, binomial, and I've gone to the binomial CD. Now my calculator is a bit different to yours, but I'm going to choose an x value. Let's try 10, which is definitely going to be too high, right? Number of trials 60 and a p of 1/6. Okay, so I'm trying 10 for my C1 value. What do I get? The p is 0.58. That's way too high, right? Now I'm going to try an x value of 5. Number of trials and p are going to stay the same, right? So try and follow along on the calculator if you couldn't do it yourself. X is 5, n is 60, p is 1/6. I get 0.05. So I'm really close to the significance level, right? So let's just try one less. Let's try 4. Okay, now I've got 0.02, right? So if I do the probability of x is less than or equal to 4, that is 0.02. So that 4 is my critical value. Okay, now notice actually what I should have said here really is less than, right? Because what will actually happen is you probably won't ever be exactly equal to the significance level. You'll kind of hop over it. So when I had 5, I had 0.05 something, and now that I put in 4, I got 0.02. So it jumped over the 0.05. So it's the first time it's less than the significance level, that's your critical value. Okay, so make sure before you continue the video, you understand what I've just done here. You understand where the number 4 came from, and you're able to work it out yourself. If you carry on without understanding that, there won't be much point. Okay, make sure you ask me for help if you're not sure where that 4 came from. Okay, and then for case 2, effectively just do the same kind of thing, but use the 1 minus trick. So if the probability of x being greater than or equal to C2 is S, right, that S is the significance level, that's the same thing as saying this. And then effectively what you're going to do is just try out values until, oh sorry, hang on, let me correct that slightly. No, it should be like this. Yeah. So again, you'll just try out values until you get 1 minus s. So 1 minus s would be 95% in this case. So for that upper critical value, you're just going to try out values until you get 1 minus s, which is 95%. And it's the first value in this case above 95%, right? Because you're thinking of, if you imagine that graph of the die, that sort of hump-shaped graph, on the right side you want it to be above 95%, and on the left side you want it to be below 0.05%, at least for this specific and significant level. Okay, and then a final definition is critical region, which, if you know what critical value is, then critical region is going to follow quite nicely. So it's as simple as saying, if that's a critical value there, let's say C2, then this thing in purple describes the critical region. Okay, and likewise, your C1 over here has the following critical region. Okay, so a critical region is a number. Sorry, no, it's not. Let me go back. A critical value is a number, a single number, the red ones. A critical region is it's a region, right? It's an inequality. So the way you'd usually write it would be something like this: x greater than or equal to C2, and this one here, it's x less than or equal to C1, right? In fact, what's the smallest value? On the left side, the smallest you're going to get is 0, and on the right side, let me just rewrite this slightly, the largest value you'll get here is 60, right? That's your n. So those are the critical regions. So those critical regions are always effectively defined that way. One side of the region is the critical value, and the other side is either 0 or it's the number of trials n. Okay, so they're kind of one and the same thing. You can get from a critical value to a critical region, and you can get from the region to the value. But because they are technically two different things, one's a number and one's a set of numbers, it's important to distinguish those two words. So don't use the words critical region and critical value interchangeably. They mean similar things, but slightly different. Okay, and then this area here in the middle, the bit that's not in any of the critical regions, this we call the acceptance region. Why do we call it that? It's because ultimately, when we eventually do our hypothesis test, we're going to roll the die. We're going to roll it 60 times. We'll see how many we get. If I roll 10, if I roll 10 sixes out of 60, then that means my observation was 10. It's in the acceptance region. I stick with my H0. So this is what all of this is for. It's for deciding if I stick with H0 or H1. If I rolled, say, 12 on this diagram, it'd be about here. I accept it. What if I rolled 1 6? Now it's inside the critical region, according to how I've drawn it. That means I reject H0 and I go with H1. H1 is the die is biased. If I rolled 30 sixes, I'm all the way over here, I'm inside the critical region. So again, I would reject H0, the fact that it was unbiased, and I would say it probably is biased. It's in the critical region. I go with H1. Okay, so that's what these regions are for. They are precisely defining that concept at the beginning, which is what values are the ones where I'm going to say that die is a lie, there's something wrong with it, and which values are the ones which will say, for which I'll say the die is probably fine, I believe you, it is a fair die. If you believe the H0, the null hypothesis, it's in the acceptance region, and if you roll something, you observe behavior which is in the critical region, we'll say it's biased. We reject and we go with H1. Okay? Okay, so let's look at a specific example. We've been given that we're going to take a single observation, so we're going to do some experiment and observe a number which is taken from a binomial distribution B6P. So in other words, there's a hypothesis test going on. We're not going to do the whole test, we're just going to do the setup for it, but within this test something is being done 6 times, 6 trials, and each of those trials has a probability P of being successful and a 1 minus P probability of being unsuccessful. And we're going to observe out of those 6 trials how many times was there a success. What success or failure is in this context, we don't know. It could be a 6-sided die, it could be checking 6 Coke cans for sugar quantity, it could be 6 of anything, but we're doing some trial 6 times. And then we're told the observation is going to test the following hypotheses. The default is that the probability of a trial being successful is 0.35. That's your null hypothesis. The alternative hypothesis is that actually the probability is more than 0.35. Okay, so our test statistic is X. This is our test statistic. And I wrote down X. X wasn't in the question, so let's just use X by default. And it's modeled by a binomial 6P. So again, 6 is the number of trials, and P is the probability of a trial being successful out of these 6 times. Sorry, not out of these 6 times, out of each of those 6 trials individually has a probability P of being successful. So P, as is usual, but just to remind you, within a binomial on probability, it's going to be between 0 and 1, right? So now we're asked to set up the hypothesis test, use a 5% significance level, find the critical region. So finding critical regions really means find the critical value, and then from that you can define the region. Okay, so we're going to find the critical value. What might help at this stage is to visualize what's going on in terms of this distribution using that hump diagram, because binomial distributions always form a sort of hump. It may not always be symmetrical, but you've got some kind of hump going on. And just remember that this is the left tail and this is the right tail. Okay, and what we're being asked to do is find the critical region, in this case because it's greater than, and we can justify why this is the case, but let's just remember it as a rule. If it's greater than, we're talking right tail. If it's less than, we're talking left tail. So in this case, right tail, yeah? So we're looking at the right tail, and we want to find the specific value on the x-axis, C, which is our critical value. That corresponds to the correct level of significance, 5%. So in other words, let's write down the formula for this, or the expression, which is going to help us work this out. The probability of that random test statistic, that random variable test statistic, being greater than or equal to the critical value, and we're choosing greater than or equal to because we're on the right, that probability needs to be less than 0.05, which is our 5%. Right, our 5% significance level. So now that we've got this set up, we just need to do a bit of trial and error on the calculator to figure out what this is. Now, it's a little annoying because it's the greater than version, and on your calculators you can only do less than. But what you can do is try a number and then just work out what that is equivalently in the less than version by doing 1 minus. So what I mean by that is, if we work out what this is, that's going to be the same as 1 minus, and what's the opposite of being greater than or equal to 5? If you can only take whole numbers, it's going to be less than or equal to 4, right? So 5 and above, the opposite is 4 and below. Likewise, if we check greater than or equal to 4, it's going to be 1 minus the probability that's less than or equal to 3. And these ones in red, these we can work out on the calculator. So what I suggest we do is, let's work these out on the calculator, see what we get. Okay, so binomial CD, I'm putting an n of 6. And what about p? Well, my p is the thing we're doing the test on. By default, we pick the null hypothesis. So 0.35. That's always the case. By default, you pick the null hypothesis because it's your default position. So number of trials is 6. P is 0.35. I'm doing this on the calculator. And my x, let's try 5. Okay, so we're doing trial and error. I get 0.998. Right. Oh, sorry. No, I didn't want to do 5, did I? I wanted to do 4. Right, because I'm doing this part here. So let's do 4. 0.977. So I get 1 minus 0.977. Okay. And let's do then this one. So less than or equal to 3. So instead of 4, as my x, I put 3. I get 0.88. Make sure you follow along so you can see where you're getting these on the calculator. Otherwise you'll confuse yourself later. And in this case, let's work out then the final probabilities, 1 minus those. We get here about 0.023, and 1 minus 0.882 gives me 0.118. Okay, so what does that tell me? That tells me the probability of x being greater than or equal to 4 is 0.118, about 10 or 12, 11%, right? 11.8%. So that's not within the significance level yet, right? We're not below the significance level like we want it to be. So the critical value is not 4. Then we look at 5 and we follow our process and we got 0.023. 0.023, that's about 2.3%. It is in fact below. So that's our critical value. It's the first value at which getting that result or worse or higher, in this case, to the right, has a probability lower than the significance level. So our critical value, our crit val, C is equal to 5. Okay, and then part B says what's the actual significance level of this test. Oh, sorry, before we go to B, we didn't actually finish off A, did we? I wrote the critical value, but what's the critical region? The critical region, remember, is on the diagram here. If this is 5, C equals 5, then it's everything that's 5 or more. Right, that's the region. So think about how many tests there are. There's 6 tests, and I just said 5 is the critical value. So the critical region is anything that's 5 or above. So in other words, 5 and 6. That's the only possibilities. So the critical region is, we can write it a couple ways. We could either say x is between 5 and 6. So it's greater than or equal to 5, it's less than or equal to 6. Or we could just say x equals 5, 6, and that is quite clear as well. When it's a small amount of numbers, you can just list them. If it's a larger range, write it as a range. Okay, but ultimately the critical region is a set of values. It's the critical value and also everything, in this case, above it. And then just keep in mind, throughout all of this, we've always been working with the right tail. If the only thing we did to this question was flip that greater than to a less than, then the question would change to working with the left tail, which would mean these calculations would be a bit easier because we'd actually flip this greater than or equal to a less than or equal to. This would stay the same. And then we'd actually be finding a critical value here. And then our critical region would be everything that's at that value or below. Okay. So this example, we're just doing one type of one-tailed test. There is the other type of one-tail. Keep that in mind. Okay, so then part B, state the actual significance level of this test. The actual significance level is simply the actual probability that corresponds to that critical value. In other words, that critical value or above, what's the probability of getting a number in the critical region? Right? So we said we wanted it to be less than 0.05, but because we're using whole numbers, we'll never exactly get 0.05. So the first time it's below, that's our significance level, right? Remember, a significance level is a probability. So with that said, if you've understood what I've been saying, can you pick out the actual significance level on this screen? There's a number on this screen, which is the answer to B. Which one is it? Okay, and the answer is this, it's 0.023. Right, that's the answer, because that corresponds to the probability of this, which is greater than or equal to the critical value. Okay, so that's our answer, 0.023. Okay, again, any confusion, ask now before we move on. You're going to have plenty of time to ask questions, so make sure you do ask. Anything about this you didn't like or didn't quite understand, get it clarified and then move on. Okay, so let's move on. Okay, so far we know in theory how to get a critical value / critical region if you are given the significance level and the details of the distribution, the binomial. However, throughout all that, we've been using the assumption that we're working with a one-tailed test, right? If it's a two-tailed test, it's almost the same, but different. So if you're working with a two-tailed test, then this is what you need to do. Or let's visualize it first. So in a two-tailed test, right? Remember our tails are effectively this part here, the left tail, and this part here, the right tail. Okay, and remember this sketch is, I mean here it's just a sketch, but it refers to a real thing. The example we had of the die meant that x-axis is our random variable, our test statistic, and y-axis is the probability. It's the same here still. Right, it's always the same. X-axis is the statistic value, Y is the probability. So that's what we're showing here. The left tail is that region there, the right tail is that region there, roughly speaking. And then to be specific, we're going to say C1 is here and C2 is here. Now, before, what we did was, in one tail, we picked one of them and then worked entirely with that. With a two-tail test, you effectively have two critical values and two critical regions, and you use both of them. And what you basically do is you say the probability of x being greater than or equal to your C2 is now, instead of equal to the significance level, it's equal to the significance level divided by 2. And I think we talked about that last time. So it's like that. And the probability of x being less than or equal to your critical value 1 is also equal to s over 2. So for instance, if it was a 5% significance level in the question, you would change that to 0.025 or 2.5%. And then you'd work out your C2 and your C1 according to this. In fact, I think I'm just going to summarize it here to make it clear. This is the two-tail set of formulas you should remember. Right? I mean, it summarizes the concept really, but if it helps to just remember it as a formula, then you should do so. And then for one tail, we're basically saying pick one. So here you do both, whereas for the one tail, only one of them actually applies. So let's just call it C, and it's equal to S. Right, and you're only going to pick one critical value. And in this case, you choose one. And the one you choose has to line up with the hypothesis. So for two-tail, your alternate hypothesis will always be a not equals on the population parameter. You pick this. For one-tail, it'll either be greater than or less than. If it's greater than, you pick this. If it's less than, you pick this. Okay, so hopefully that makes sense, because in both cases, the total probability of the critical regions adds up to the significance level. Here you take both, and S over 2 plus S over 2 is S. And here you just pick one, and the probability is S. Make sense? So that's it. That's the only difference really, is that process we just did before. You're going to divide the significance level by 2. And also, you may, if you're working out critical values, you may need to find 2 of them. Again, as we'll see next session, in the end, you might end up only actually having to work out one anyway. But which one you choose is a story for another time, right? But for now, just make sure you understand that you divide by 2 the significance level when it's a two-tailed test, and use this version rather than this version here. Okay, so let's look at an example to clarify this one. Okay, so let's look now at a case where we're going to use the two-tail scenario. How do we know this is a two-tailed question? Just looking ahead a bit, the population parameter has an alternative hypothesis using the not equal sign. So that all by itself tells me it's two-tail. So we have a random variable x. It's distributed by a binomial b with a number of trials 40 and a probability of each trial being a success p. We're going to use a single observation which is going to test the hypothesis with a null of 0.25. So by default, we assume each trial has a quarter probability of occurring, of succeeding, and 3/4 failing. And then the alternative hypothesis is that actually, what if it's not 0.25? Perhaps this random variable, whatever process it's describing, doesn't actually have a probability 0.25. It's biased or it's different in some way. Specifically, it could be higher or lower. So now using a 2% level of significance, we're going to find the critical region of this test. Okay. This extra bit here, by the way, this is just redundant information. The 0.01 simply comes from halving the 2% and converting it to a decimal. But we already know we need to halve the 2%, don't we? So you won't be told that usually. If it's a two-tail, you need to recognize it as such and then divide the significance level by 2. So let's do that. S equals 2%, our significance level. S over 2 is equal to 1%, which is 0.01. So that's the value we're going to be using. And within our two-tail, our right tail has the following property, which is that the probability of the random variable being greater than or equal to a critical value, let's call it C2 for the right, that needs to be smaller than 0.01. And the probability of it being less than the left critical value, so we're on the left tail, also needs to be less than 0.01. Okay, so we need to find out what these two values are, these two critical values. Once we've got the two critical values, we can find the critical region. Okay, so here we're using both, and remember we had to halve the significance level in this case. If it was one tail, it would be 0.02 here, and we would just be picking one of these. Right, so let's start with the left tail, because I think that's a bit easier. We're going to, in our calculator, go to distribution binomial CD. The number of trials is 40. The P I'm going to default at 0.25. And then my X value, that's up for me to try. So let's try 5. So here's what I'm trying now. I'm trying out what is the probability then it's less than or equal to 5. And I get 0.04. Okay, too big. Let's try less than or equal to 4. I get 0.016, still too big. Let's try 3. And I get 0.004. So that is sufficiently small now, isn't it? 0.0046, or rounded 47 is what I get there. So that is the first time that it's gone below the 0.01 value, which means my critical value is indeed 3 for the left tail. Okay, so let's write this as C1 equals 3, which is my left tail. That's my left critical value. In terms of that sort of hump diagram, like with the die, that's saying that you've identified your critical value here, C1 equals 3. So now we need to find the other one, right, the C2, which is what we're going to have to try and find here. So let me just remove this working, and we'll try and do that one. It'll be a little bit more tricky because we've got the greater than situation here. So what I would suggest is, first, before we start this, because we're going to be doing trial and error, let's think about what would be reasonable. So if I did something 40 times, and the probability of each time, each trial being successful is 0.25, how many successes are you going to expect out of 40? If I do something 40 times and each time it has a quarter chance of happening, I would say about 10, 40 times a quarter. So that means 10 is probably the most likely outcome. So the 3 is significantly less than 10. So now we have to think what would be a little significantly above 10. So we don't have to necessarily go all the way to 20 or 30. Remember with the die doing it 60 times, it was already at about 20 when we hit the upper critical value. So let's do a guess that's not too close to 40. Let's try maybe, I mean, we could just start with even 15. Let's try 15. So let's try probability that x is greater than or equal to 15. And what's that? That's the same as 1 minus the probability that it's less than or equal to 14. So on the calculator, Let's work that out. Number of trials is still 40, p is still 0.25, and my x, I put in 14, I get 0.9455. So 1 minus that is equal to, if we do that in our heads a bit, about 0.15. I'm being approximate here because I just want to get close to 0.01. Clearly too big. Okay, let's try 16. But actually quite low, right? You're already at the 10% mark. So probability of it being bigger than 16 is the same as it being less than or equal to 15. 1 minus that it's less than or equal to 15. So let's put in 15. N is 40, P is 0.25, X is 15. I get 0.9737. Okay. So that means I'm still not there. That's 0.02. But getting close, probably in the next one. Incidentally, you don't necessarily always have to jump by 1 each time. It's a trial and error thing. You can search it out however you like, but just make sure that you find the first one where it happens. But I think we're probably going to get there next time. Let's try it up here. Probability that it's greater than or equal to 17 is 1 minus less than or equal to 16. Let's try it. So I'm doing binomial CD, N40, P 0.25, X of 16. I get 0.988. So 1 minus 0.988. Close. That's 0.012. So we're almost there. We've almost dropped below 0.01. Let me just remove this and we'll do hopefully what is to be the last one. Greater than or equal to 18. Is this going to do it for us? Let's see. So less than or equal to 17, 0.995, which is indeed less than 0.01. It's about 0.005. So I've been a little bit approximate with these decimals I've written. I've just used sufficient decimal places to conclude either it's above 0.01 or below 0.01. So we've done it. That's our C2, right? When it's bigger than or equal to 18, the probability of it happening is less than 0.01, which is half the significance level. So C2 equals 18. That's our right tail. Okay. So again, in terms of the hump diagram, which is not a technical term, we've got C13 on the left, our critical value C2 18 on the right. The region is everything over here and everything over here. So what will that be? Remember, the values we can take with 40 trials is 0 to 40. We've got the acceptance region in the middle and the critical regions. There's 2 of them, and we combine those to get a single critical region. So the critical region is when x is 3 or lower, or x is 18 or higher. So that's going to be our final answer. Let's write it over here in purple. X is less than or equal to 3, and x, so I'm answering part A here, is greater than or equal to 18. And also we should state the other bounds, right? It's less than or equal to 3, but the minimum it can be is 0. So let's put that there. And on the other side, what's the maximum it can be is the number of trials, which in this case is 40. So let's write that there. Okay, and perhaps you want to sort of flip that one, write it the other way around. In fact, I will, just so that it's not so confusing looking. It runs from 18 less than or equal to x up to 40. This is our critical region. So we took the 2 critical values, 3 and 18, created our critical region. It's technically 2 regions, but we combine it into 1. Okay, so then before we look at B, If this was a real hypothesis test question, it might then say, oh, the 40 trials were performed and it was observed that there were 2 successes. So then you would say, oh, 2 is within the critical region, I go with H1. If, for instance, you've got 5, you would say, oh, 5 is not in the critical region, therefore I go with H0, right? Because it's in the acceptance region, I accept H0. Okay, so that's what the point of doing this is. Unfortunately, we're just not going to get there, or maybe fortunately for the sake of time. So that's it. That's finding the critical region for the two-tailed test. Finally, write down the actual significance level of the test, right? What we're going to do is find the probabilities of these 2 regions, but we've basically done that, haven't we? The probability of it being greater than or equal to 18, our critical value, was this 0.005 number, and the probability of it being less than or equal to 3, I've lost that now, but we can work that out again. But effectively, the answer to B is going to be as follows. It's going to be, take the actual probability of it being less than or equal to 3 and add the actual probability of it being greater than or equal to 18. For the greater than or equal to 18 case, it should be this number here. Looking at the textbook, it seems actually that the numbers might be a bit incorrect. So I'm not going to report the ones I see there. For probability of x less than or equal to 17, in the textbook it seems to get 0.9884, which disagrees with my 0.995 here. I have double checked, I do seem to be getting 0.995, so just be aware of that. I think they may have made a bit of a mistake there. But regardless, this method here is the correct one, right? The actual significance level is the probability of the critical region. Because you've got 2 regions, find out the probabilities of them separately. And in this case, that first part is quite easy. Put 3 in the calculator, you'll get a decimal. And that second part, we're going to do 1 minus, and what's the opposite side of greater than or equal to 18? It's less than or equal to 17. So you'll put 17 in the calculator, do 1 minus, and add that onto your previous number. That will be the actual significance level of the test in this case. Okay, cool. All right, so it's been a long one. You've got a chance to do some questions, and I think very importantly, a chance to use the time to ask for help with anything we didn't understand or for further clarification. I think within this topic there's a lot of different concepts, and sometimes it's difficult to know which one to teach first and which one to teach next. So it could sometimes be the case that the ordering is just a bit off sometimes. So if you are still confused about something, don't worry about it. Just make sure you take action on that, namely ask me for help as soon as you can if you don't understand what's going on here exactly. If you want a term defined, or you want an attempt to re-explain something. Okay. If you think you're ready to give it a go, do have a try these questions. There's 3 here and then 1 on the next slide. First one is just asking you to make sure you understand what each of these terms mean. In all likelihood, you may have some idea, but then may not be precise enough. So make sure you check at the back of the Year 1 Applied Book 7b, make sure your wording matches the textbook's wording, and if it doesn't, make sure you understand what the textbook's answer is trying to tell you. Okay, then have a go at 2, which is a nice basic attempt to find critical values and a critical region for a one-tailed test, and then see if you can do the same for a two-tailed test. There's one more question on the next slide as well. Okay, you can pause the video now. Okay, and then finally here, we have got an exam style question. You need to interpret, is it one tail, is it two tail? Make sure you describe the test statistic correctly, describe the hypotheses correctly, and then the only bit that's actually calculation is this part where we find the critical region. Okay. Oh, and then the actual significance level is also a bit of calculation. So have a go at that, and then if you finish and you do have time, what I suggest is within the textbook and within these pages, it's page 103, 104. A lot of the questions are pretty similar, and you'll find that's the case with hypothesis testing, more so than any other topic. The questions are really repetitive, but if you can't do any of them, then it's a problem. So you want to be able to do at least one of these critical region or critical value questions correctly, and then as confirmation, maybe just do one more. So I would advise, if you have time and you haven't needed to ask for help as much, then try and answer at least one more from the textbook, page 103 and 104. Double check that you do actually know what you're doing, rather than just seeing the answer in the textbook and convincing yourself that you knew that would be the case. Okay, try and do at least one by yourself, and then have it confirmed correct. Okay, cool. All right, so that's it. Good luck with it, guys. Let me know if you need help. Pause the video now.